In this video, we'll give an explanation of this formula on the screen, which gives us a way to calculate the Laplace transform of the derivative of a function in terms of the Laplace transform of that function itself. So in order to do this, we need the definition of what it means for a function to be of exponential order, and that's just given here on the screen. So roughly speaking, a function is of exponential order if it is dominated by an exponential function, and all of the usual functions are of exponential order. Any polynomial, sine, cos, and so on. And the important thing about these kinds of functions are that they always have Laplace transforms. And so this is the main property that we'll be interested in. So given any function of exponential order, that's all. Knowing only that, we know that it will have a Laplace transform. Okay, so let's revisit this formula here. This formula is, so from first principles, if we were interested in calculating the Laplace transform of the derivative of a function f, then this is from first principles exactly what we get. And you see on the right-hand side here that we're taking the integral of the derivative of a function multiplied with some other function. So this reminds us of a technique. We know how to integrate, when we're given such a situation, we know how to integrate such functions. We can use integration by parts. So the formula for integration by parts is just given here. The integral of u prime v is just u multiplied by v minus the integral of u v prime. So to integrate this kind of left-hand product, one must just choose what is u prime and v and determine v prime and u, and then this formula applies directly. Okay, so using integration by parts, the derivation of our the formula that we're interested in is just given here. And this formula, so at the very end formula, can only be concluded if we know that f is of exponential order. So that's where in our derivation we use that f is of exponential order. If you see in the third line from the bottom, the f of b, the term f of b e to the negative sb, that vanishes as b goes to infinity. And that's where f being of exponential order is used. Okay, so the formula that we end up with is just given here. And the question that you're likely interested in is how can we use this in practice? What good is this formula? Okay, so let's get into that. So we have our formula here, and let's use this to solve an initial value problem. So here's our initial value problem. It's a very simple one, but we're just going to illustrate the technique here, how we can use how can we use Laplace transforms to solve these kinds of initial value problems. Okay, so to solve this initial value problem, we're going to apply a technique from the very first video on Laplace transforms. What we're going to do is apply the Laplace transform to the left-hand side and to the right-hand side. So since we're starting with this kind of equation, we know that we apply the Laplace transform to the left-hand side. It must be equal to the Laplace transform of the right-hand side. And the point is going to become clear once we do that, because if I take the Laplace transform of y minus y prime, as I said, this must be equal to the Laplace transform of 1. And we can use general properties from here. So firstly, Laplace transform is linear, so we immediately have this. And we know the Laplace transform of the right-hand side because it's just, we have a table. We've already, one of the points of the technique of Laplace transforms is that we can tabulate various Laplace transforms and then use them whenever we need them. So here we are. We have this Laplace transform of 1 just equal to 1 over s. Good. So here we can just write 1 over s. Okay, good. Now in this kind of situation, we have the Laplace transform of y minus the Laplace transform of its derivative. And now we can use this formula that we just derived. The Laplace transform of the derivative of a function is just equal to s times the Laplace transform of that function minus that function evaluated at 0. Great, so we apply that formula directly here and just simply get s times the Laplace transform of y minus y of 0. So that's just applying the formula directly. Then we must get 1 over s. Great, so here we can just simplify a little bit. And so we're just going to get L of y times 1 minus s is just equal to 1 over s minus 2. Okay, good. So now, once we've done this, the technique is to always solve for L of y. So let's do that. So here, we're going to have so we're going to have that L of y is just equal to 1 minus 2s all over s times 1 minus s. And here we can actually simplify this. We can do a partial fraction decomposition here. So the idea now at this point is to try and get this, the right-hand side here, to look like a linear combination of these kinds of functions that you see on the in this table. And the reason for that is then because if that's the case, then we can apply the inverse Laplace transform. Okay, so to do that, let's try and break up this denominator here. Okay, so we're going to get 1 minus s all over s 1 minus s. So just doing this here, and then what do I get now? I just get 1 over s minus s over 1 minus s, and this is just equal to 1 over s plus, sorry, not s here, this is just 1. So I cancelled off the s here. That's how I got the 1 over 1 minus s. Okay, good. So here the minus then can swap the denominator around like this, and so we're left with this. Okay, so we end up just getting that the Laplace transform of our function is just 1 over s plus 1 over s minus 1. And those two functions are of this form here. So 1 over s is here, and then 1 over s minus 1 is of this form. And so we can immediately say that if we take the inverse Laplace transform of both sides here, well, firstly, the inverse Laplace transform of L of y is of course just going to be equal to y, but this must be equal to the inverse Laplace transform of 1 over s plus 1 over s minus 1. And by what we just said, since we've identified these two functions here and here, we can then just write out that this will be 1 plus e to the t, because alpha in this case is just going to be equal to 1. Okay, in the next video we'll be looking at higher versions of this formula. So of course you can imagine what happens in the generalization of this kind of formula, which is to say, what happens if I had a second derivative here, or a third derivative, and in general an nth derivative. And we do have a corresponding formula, and that's going to be the topic of the next video. Okay, thank you.